Good morning, afternoon, or evening, everybody. My name is Luke Kruse, and today I'm going to be presenting the MSEN 660 Journal Presentation number 3 on a paper which does a remarkable job demonstrating the utility of convolutional and recurrent neural networks. The paper is titled Finding the Optical Properties of Plasmonic Structures by Image Processing Using a Combination of Convolutional Neural Networks and Recurrent Neural Networks. With this, thank you so much, and let's dive right in. This paper was published back in 2019 in the journal Microsystems Nanoengineering, a journal of Nature. The authors, Iman Sajedian of Sherbrooke University, Jungyoung Kim of Kwangwon University, and Jungsuk Roh of Pohang University of Science and Technology, together worked on this paper to demonstrate the power of convolutional and recurrent neural networks, their ability to classify and predict the absorption spectra of plasmonic bodies. This work was financially supported by the National Research Foundation. So before we dive real deep into the details of this paper, let's first take a quick 30,000-foot overview of what the authors were able to accomplish. So starting with these 2D images of these plasmonic nanostructures, they were able to use these 2D images along with the simulated absorption spectra corresponding to each of these images and incorporate them into a convolutional neural network for basically analyzing the 2D geometries and then correlating using the RNN to find what the output absorption would be. Now, let's go ahead and consider the motivation or the driving force behind this research and ultimately why the use of these deep learning models can be so powerful. So, in recent years, nanofabrication and plasmonic research has become a lot more accessible. Our ability to design these nanoscale patterns has become a lot easier, and likewise, the design of these kind of plasmonic bodies has also become more accessible to labs all around the world. And as one could imagine, and looking at these pictures that we have from these kind of toadstool structures on the right to the whole nano patterns, that each of these have their own kind of plasmonic responses and plasmonic properties. And this leads to a really complex and diverse design space with these very large data sets. As each knob that you turn from the pitch between these holes or these patterns to the ultimate size of them has a very complex relationship with their optical properties. And so because of this, because we have high dimensional data and a ton of data, and because the design and fabrication of these structures is not yet cheap, the use of machine learning is very desirable for this particular field. All right, so to be able to run this model, let's look at the data flow and the preparation that our authors took. So essentially the way this data was for testing and training was first generated was they started with creating different kind of random shapes of plasmonic bodies. So namely, they started with a substrate, which was glass in this case, which you see here in purple. And then with these random geometries, these structures of silver, which we see in the yellow. So they varied in basically all 2D geometric features. However, for the actual modeling, these plasmonic bodies were modeled to be about 50 nanometers tall with lattice constant or a kind of an X and Y separation of about 500 nanometers in kind of like a square lattice. And the source polarization is fixed. Now, these things were all things that are the plasmonic responses are very sensitive to, but beyond that, they were varied in all other geometric qualities. So the number of shapes in each structure, this was kind of chosen randomly from being anywhere between 1 and 6 shapes per body. The type or the shape itself from triangles, rectangles, squares, all these kind of little subshapes that you see within this image here, as well as the position X and Y that you see in kind of each of these cells. And beyond that, the rotation, flipping, all sorts of these things could be done to further modify. And essentially, what our authors ended up with was over 100,000 or about 100,000 different plasmonic structures that were all then simulated, and their optical absorption response was then collected using Lumerical, which is a plugin for ANSYS. And it's important to note here that the actual images themselves here are 100 by 100 pixels. This was done just because higher fidelity didn't really lead to any more accuracy, but it should be noted that for the actual simulation to get the optical response, they used mesh size and weren't confined by the 100 by 100 pixels. And another thing that's important to note is that the simulations here predicted the absorption spectra. Now, this could have been tuned for other spectra, whether it's transmittance or reflection or whatever it may be, but in this case, they primarily examined the absorption spectra. Now, you could imagine that there is a great deal, pretty sturdy computational load here. And to prepare these simulations, a CPU with about 28 different 2.6 gigahertz cores were used. And the simulations took about 15 days, about 2 weeks to run the simulations to get all these spectra that you see for all 100,000 samples. And then for the actual to run the model, the deep learning model itself took about a week to run once all the data was collected, and they split the data, of course, in the standard 60% was for testing, training, 30% was for training, and final 10% of the data was for validation. So once the 2D images of the 3D plasmonic bodies were created and the simulations of the corresponding absorption spectra were also made, the data was ready to be put into the model itself. Now, this model was created using the Keras and TensorFlow packages in a Python environment, much like what we've done in Emissian 660. And now, with this model, there's a lot of optimization to be done, namely, they had to optimize the number of convolutional layers, the number of nodes in each convolution layer, the shape and strides used in the convolution layers, layout of the layers, and so on. There was a lot of different knobs to turn, and they settled on using about 500 epochs. And you can see in the top right a actual flow of the different layers themselves. This is a relatively large model, and with it taking over a week to run, it's understandable to see why it took so long, but the results are well worth it. So as I just mentioned, the model was pretty darn successful, predicting almost all 10,000 of the validation data points with extreme accuracy, almost being spot on. And we see those here in the blue and orange lines comparing the simulated and the deep learning methods, respectively. And ultimately, I think really what this talks up to is just the quality of data that was given into this model, with all 100,000 data points being at their disposal, with high enough fidelity and really kind of this binary system of having glass and gold. They're able to get really accurate data. And as you see in the top left corner, the training loss was really impressive. I think getting down to the 10 to the negative fifth. That's pretty darn impressive at the 500th epoch. Though, as you can see, it does do a pretty good job even down up to the 100th epoch. And likewise, if you see the computational time, you'll notice that ultimately the machine learning model took an order of magnitude less amount of time between each of the structures. And I think that says something for the utility of this feature, being able to run through all these different structures in seconds ultimately makes for a pretty handy tool. And again, kind of touching again on the application to different parameters, things like changing the height, changing of the plasmonic body, changing the chemical identity, as I previously mentioned. These are all things that could eventually be tuned and changed in this model, and I think would make for a really interesting further discussion. So in the end, this paper demonstrated a broadly applicable and tunable model that showed that it was very capable of predicting spectra of plasmonic patterns. It was able to do this with very high accuracy and was even able to give data pretty quickly and being able to run in less than a second to predict the spectra of a given plasmonic pattern. Now, this is a wonderful tool, and I think there's a lot of great research that could be done further to better demonstrate the utility of this CNN and RNN application. A big one that I think would be a really good use of this model would be actually inverting the flow and using this same type of setup to guide the design of various plasmonic patterns for a given spectra. Typically, throughout the plasmonic literature, the way the typical workflow goes is a pattern will be proposed, and using classical electrodynamic equations, Maxwell equations, the spectra would then be modeled from that specific system. Now, I think with this paper, however, lends itself to being able to design various plasmonic patterns for a desired spectra, and coupling this with the tunability for different materials, different combinations of materials, I think could be a great tool for further research. Another update that I would like to see be accomplished would be updating this same exact model, but with various different lattice parameters, and even applying a quantum corrected model to accommodate for tunneling effects, as those lattice constants and separation between various plasmonic bodies reduces down to beneath about 10 nanometers. Tunneling effects, non-locality effects start to take place, and seeing this be accommodated for and potentially modeled and utilized to design certain spectra would be quite the interesting use of such a platform. Finally, I think a really interesting quick test that I would love to see would be the validation through an experimental result, namely devising a pattern, running it through this simulation, and then creating it. I think that this work has lent itself very well, and I would love to see it applied to more plasmonic systems. And with that, I would like to say thank you all so much. This has been journal presentation number 3, another dive into a wonderful paper, and I would like to thank you all, the viewers. Have a wonderful rest of your day, and take care. Bye-bye.